Hey there, science fans! Today, we're diving into the electrifying world of electricity. Have you ever wondered what makes the current flow in a circuit? What gives it that initial push? That's where electromotive force, or EMF, comes in. Think of EMF as the driving force behind electrical circuits, like an invisible hand pushing those tiny charged particles called electrons along. EMF is measured in volts, just like the voltage you see on batteries, but there's a subtle difference. While voltage is a more general term for electrical potential difference, EMF specifically refers to the energy provided by a source like a battery or generator. Without EMF, our world would be a much darker place, literally. No phones, no lights, no computers, you get the picture. So buckle up as we explore the ins and outs of EMF, from the inner workings of a simple electric cell to its real-world applications. Get ready for an electrifying journey. Let's get down to the basics. Imagine a simple electric cell, like the ones you find in a flashlight. It might seem like a simple device, but inside, it's a hub of chemical activity that generates EMF. A typical cell consists of two different metal strips called electrodes, dipped into a conductive solution called an electrolyte. One electrode, called the anode, has a negative charge. The other, called the cathode, has a positive charge. The electrolyte, often a salt solution, allows charged particles called ions to move between the electrodes. This movement of ions is crucial for creating EMF. Think of it like this. The anode is like a crowded bus stop with too many electrons. They want to get to the cathode, which is like a less crowded park where they have more space. The electrolyte acts like the road, allowing the electrons to travel from the anode to the cathode. Now let's talk about how this setup actually generates EMF. The key lies in chemical reactions happening at each electrode. At the anode, a chemical reaction releases electrons into the electrolyte. These electrons want to flow towards the cathode, where a different chemical reaction accepts them. This difference in electron concentration between the anode and cathode creates an electrical potential difference, which is our EMF. It's like a slope, where electrons naturally want to roll down from the anode to the cathode. The higher the chemical potential difference between the electrodes, the stronger the EMF. Different combinations of electrodes and electrolytes produce different EMFs. For example, a cell using zinc and copper electrodes with a salt solution electrolyte will generate a different EMF than a cell using lithium and manganese dioxide. Section 4, Open versus Closed. The circuit's impact on EMF. Here's a crucial point. The EMF of a cell is a characteristic property of that cell determined by its chemical makeup. However, whether or not this EMF actually drives a current depends on whether the circuit is open or closed. Imagine a battery with its positive and negative terminals unconnected. This is an open circuit. While the battery still possesses EMF, there's no path for the electrons to flow. It's like having a charged hose with the nozzle closed. The pressure is there, but no water flows. Now connect the battery terminals with a wire, creating a closed circuit. Now the electrons have a path to flow from the negative to the positive terminal, driven by the EMF. It's like opening the nozzle of the hose. The pressure now pushes the water out. Section 5. Resistance is key. Understanding internal resistance. However, the story doesn't end there. Just like that hose might have some internal resistance to water flow, even the best batteries have some internal resistance. This resistance arises from the materials inside the battery itself and opposes the flow of current. Think of it like this. The electrons flowing through the electrolyte and wires encounter some friction along the way. This friction is internal resistance. It's important to remember that internal resistance is always present, even in ideal batteries. Internal resistance is measured in ohms and plays a crucial role in determining how much current a cell can actually deliver. The higher the internal resistance, the more energy is lost as heat within the battery, and the less energy is available to power the external circuit.